Hi friends, in this session we will discuss about different types of combination of resistors. Mainly resistors can be combined in two ways, one in series and the other in parallel. Now let us have a look how resistors are connected in series. You see here you can see three resistors R1, R2 and R3. They are connected in a series. These connections are called series connection. Why? Because here one resistor is connected to the end of the other one, or you can say here resistors are connected end to end. So this type of connections are called series connection. Now the other one shows parallel connection. You see here we have taken three resistors R1, R2 and R3, and those three resistors are connected together between the point X and Y. That's why we say that these resistors are connected in parallel. Now let us discuss about series combination in detail, and let us see what happens to the total current and what happens to the equivalent resistance or total resistance when resistors are connected in series. You see here we are given three resistors R1, R2 and R3, and in the circuit you are given an ammeter. You see ammeter shows a reading. Now if you place this ammeter in between R1 and R2 or in between R2 and R3 or anywhere in the circuit, the ammeter will give you the same reading as it is placed in the original position. That means in a series circuit, electric current remains the same. Wherever you keep this ammeter in the circuit, what will be same? Current reading will be same. So in a series circuit or in series combination, we say that electric current remains the same. Now let us take a voltmeter and let us find the potential difference across these three resistors. For that we keep or we connect the resistors between the points X and Y, or we keep the voltmeter connected at X and Y. Now the voltmeter shows a reading. Let the voltmeter reading be V. So V be the voltmeter reading in this case. Now you place the voltmeter across the resistor R1. Then the voltmeter will give you another reading, let it be V1. Now if you place the voltmeter across the second resistor, that is R2, the voltmeter will give you another reading, let it be V2. Similarly, when you place the voltmeter across R3, it gives you a reading, that is V3. Now you can see that if you add all these potential differences together, that is V1 plus V2 plus V3, when you add V1, V2 and V3, that will be equal to the total potential difference in the circuit. That is V equals V1 plus V2 plus V3. What is V? V is the total potential difference across these three resistors. That's a voltmeter reading that you got when you placed the voltmeter at the points X and Y. Okay. Now what is V1, V2 and V3? V1, V2 and V3 are the voltmeter reading when you place the voltmeter across R1, R2 and R3. So total voltage or potential difference V equals V1 plus V2 plus V3. Now let us apply Ohm's law here. What is V, capital V, or total voltage? V equals IR. What is the current flowing through the circuit? That is I. Now what is the total resistance? You see these three resistors R1, R2 and R3 can be replaced by a single resistor Rs, such that Rs is equal to what? R1 plus R2 plus R3. So we have already got the relation that V equals V1 plus V2 plus V3. But when you use Ohm's law or when you apply Ohm's law, what is V? V equals IR. Now what is V1? V1 is the potential difference across the resistor R1. So applying Ohm's law, what you will be getting? V1 equals IR1. Why I? I because it's a series combination, the current remains same throughout the circuit. So the current flowing through R1 is I. So voltage V1 equals IR1. Resistance is R1 and current is I. So V1 equals, applying Ohm's law, you will be getting V1 equals IR1. Similarly, what is V2? IR2. What is V3? IR3. So we get IRS equals IR1 plus IR2 plus IR3. What is common? I is common. So that get cancelled and you will be getting Rs equals R1 plus R2 plus R3. That means when two or more resistors, when they are connected in series, the total resistance Rs equals sum of the individual resistance, that is Rs equals R1 plus R2 plus R3. So here the total resistance will be always greater than the individual resistances because Rs equals R1 plus R2 plus R3. Now let us see what happens to the total resistance or equivalent resistance when these resistors are connected in parallel. Now let us have a look at the figure. You see here three resistors R1, R2 and R3 are connected in parallel. Now ammeter is also connected here. Now you take a voltmeter and find the potential difference at the points or between the points X and Y. Now the voltmeter will give you a reading. Let the voltmeter reading be V. V is the voltmeter reading. Now if you place the voltmeter across R1, you can find the voltage or potential difference across R1. That will be also V. If you place the voltmeter across R2 and R3, you will be getting the same potential difference. That means when resistors are connected in parallel, what remains the same? The potential difference remains the same. But what about current? You see here the ammeter will show you or give you a reading. Now if you keep this ammeter near to R1, the ammeter will give you another reading, let it be I1. Now if you place the ammeter near R2 or in the second branch, there also ammeter will show you another reading. Now if you place in the branch or close to R3, you will be getting another current passing through that branch, let it be I3. Now if you add I1, I2 and I3, that will be equal to the total current passing through the circuit. That means I equals I1 plus I2 plus I3. Now let us apply Ohm's law here. See what is total current I? I equals V by R. What is V? V is the potential difference, that is V. What is R? R is the total resistance. Here let the total resistance be Rp. Rp stands for parallel because here resistors are connected in parallel. Equals, so V by Rp equals, what is I1? According to Ohm's law, I equals V by R. Here what is the value of V? V is V itself. But what is resistance of the first one? That is R1. So I1 equals V by R1. What is I2? V by R2. What is I3? V by R3. So the equation becomes V by Rp equals V by R1 plus V by R2 plus V by R3. You see V is common, numerator is common. That get cancelled. Now you will be getting 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. That means when two or more resistors are connected in parallel, the reciprocal of the effective resistance will be equal to sum of the reciprocal of the individual resistances. That is 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. You see, in this session we discussed the total resistance when resistors are connected in series, and we found the total resistance when resistors are connected in parallel. These two derivations are very important because from these two any one can be expected for your examination, or you will be getting some numericals from this particular topic. Here you remember, when you connect resistors in series, what remains same? Current remains same, but what is different? Voltage is different. So V equals V1 plus V2 plus V3. Just apply Ohm's law and substitute V equals IR. Then what is V1? V1 equals IR1, V2 IR2 plus V3 IR3. I get cancelled. You will be getting RS equals R1 plus R2 plus R3. What is RS? S stands for series. When resistors are connected in series, total resistance RS equals R1 plus R2 plus R3. But when resistors are connected in parallel, what remains same? Voltage remains same, but what changes? Current changes. You see, here total current I will be equal to I1 plus I2 plus I3. Apply Ohm's law, I equals V by R. Then V is common, it gets cancelled. You will be getting 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3. So you have to by heart, or you should know how to derive these two relations. It is a sure question for your examination. We have seen that when resistors are connected in series, same current flows through all the resistors. Now let me ask you a question. Can you connect a small bulb and an iron box or an electric heater in series? No. Why? Because these two components require different amount of current. But when these are connected in series, all these equipments or these components get the same current. So that is the one disadvantage of series combination. In series combination, all the equipments, if you connect some equipments in series, all the equipments will be getting same current, but that is not practical. Now the next disadvantage is, if any one of these instruments or equipments connected in a series gets failed, the remaining equipments also stop working. Why? Because all these are connected in series. So these are the two disadvantages of series combination. First one, here through all the equipments the same current passes, but that is not practical. That is the first one. The second disadvantage is that if one of the instruments fail, the other equipments also stop working. So that's why we use parallel connection or parallel combination in our wiring. In parallel combination, or when you connect the equipments in parallel, we have seen in a parallel combination, the current is different through different branches. So each equipment or each gadgets can get its own or can consume its own current. The second advantage is that when resistors are connected in parallel, the effective resistance of the circuit get reduced. So because of these two reasons, we prefer parallel combination or parallel connection over series connection.